On July 8, 2000, a U.S. Marine Corps C-130 cargo plane initiated a paradrop over the high Canadian Arctic. The payload was heavy, and at an altitude of 1,000 feet, the parachute separated from the cargo. Without the drag of the canopy, the pallet hit the ground at terminal velocity. The impact entirely destroyed a specialized construction crane, a heavy transport trailer, and custom fiberglass floors, required to build a multi-million-dollar simulated habitat. The immediate logistical fallout was severe. A paid construction crew was suddenly stranded in a remote, freezing desert with no equipment, leading the project's manager to resign and abandon the site just 4 days later. If a structural collapse of this magnitude had occurred 140 million miles away, the crew would have been dead on arrival. Experiencing a catastrophic loss of hardware here on Earth proves exactly why off-world construction plans must be ruthlessly stress-tested before a rocket ever clears the atmosphere. To conduct these tests, researchers need environments that mimic the hostility of deep space. Devon Island is a rocky polar desert locked in ice, located barely 1,000 miles from the geographic North Pole. This map shows the geography of the island, zooming in on the Haughton Impact Crater. It's a 23-kilometer-wide scar gouged into the Earth 39 million years ago, making the shattered rock here an incredibly accurate geological counterpart to the frozen surface of Mars. Following the parachute disaster, volunteers managed to salvage the materials and erect the Flashline Mars Arctic Research Station. The core mission architecture is straightforward. Place a small crew inside a tiny cylinder, isolate them completely, and require them to conduct complex field geology. Using this specific geological basin acts as a highly controlled crucible. Isolating crews in this environment exposes lethal flaws in human planning and habitat design long before those issues have a chance to manifest in deep space. Operating the station requires the crew to adhere to strict simulation constraints. If a researcher wants to collect a rock sample outside, they must first spend time in the airlock executing a mandatory simulated depressurization protocol. Once outside, they face the severe physical handicaps of wearing an analog spacesuit. The heavy helmets drastically reduce their field of vision, and the thick gloves cause a severe loss of dexterity, turning a basic task like swinging a geological hammer into an exhausting physical challenge. This timeline charts a radio signal traveling from Mars to mission control on Earth. Because the signal is limited by the speed of light, the crew must operate with a mandatory 20-minute communication delay, meaning no one can talk them through an immediate crisis. But while the spacesuits and radio delays are artificial, the local environment is genuinely lethal. The island is actively hunted by the local polar bear population. Because the simulated suits restrict visibility heavily, there is one strict exception to the simulation rules. Whenever the crew leaves the habitat, one member must stand watch completely out of sim, armed with a pump-action shotgun loaded with slugs. Layering artificial operational handicaps directly over genuine flesh-and-blood environmental hazards forces the crew to develop highly resilient field tactics. If their communication protocols or situational awareness fail here, the consequences are immediate. Operating under this pressure, crews have successfully deployed seismic sensors, piloted unmanned aerial vehicles, and mapped the jagged terrain, all while heavily encumbered by their suits. This diagram illustrates a chemical extraction process tested in the field. By crushing gypsum samples and heating the rock, they released pure liquid water. As this chart shows, manufacturing water on site drastically reduces the massive payload weight required to lock it to Mars. The station also functions as a psychological pressure cooker. In 2007, a crew sealed themselves inside the habitat for a continuous 100-day simulation to test the mental friction of prolonged isolation. Throughout the mission, researchers tracked the crew's cognitive performance, running continuous metrics to map exactly how their mental acuity and group dynamics degraded over time. Conquering these hardware and psychological hurdles allows engineers to map the absolute limits of human endurance, locking in the data required to keep future interplanetary explorers alive. While the geological data is substantial, these expeditions serve as a unique pipeline for the specific type of leadership required to run an aerospace program. During the 2003 expedition, the logistics and cognitive testing were executed in part by Crew 8's chief engineer, Ella Carlson. Following her time in the Arctic, she went on to defend her PhD in space technology with a dissertation focused on Mars and instructed university students in human space exploration at the European Space Agency's summer course. Her expertise eventually led to an appointment as the head of space for the Swedish Armed Forces, overseeing national defense strategies beyond the atmosphere. Today, she serves as the Director General of the Swedish National Space Agency. The trajectory from an analog habitat to national space leadership suggests that managing a field site provides the specific logistical and command experience needed for actual mission control. Over 2 decades of operation, the Flashline Mars Arctic Research Station has systematically broken equipment, tested psychological breaking points, and refined the personnel required to build an interplanetary infrastructure. When the first crews finally begin constructing a permanent settlement on another planet, their survival will rely entirely on the data generated by the people who froze, failed, and figured it out in the high Canadian Arctic. When an astronaut finally steps onto the Martian surface, they will rely on the field tactics and hardware failures first identified in the Canadian Arctic.